Bonding steel columns to the ground ring is generally required to adhere to electrical codes and ensure safety. NFPA 70, or the National Electrical Code, Section 250.104 dictates that a bonding jumper, sized according to Table 250.104C, must connect to the grounding electrode system at each building or structure where the grounding electrode conductor enters. This jumper establishes a low impedance path for fault currents, enabling them to reach the grounding system efficiently. IEEE Std 1100, also known as the Emerald Book, Section 10.310 suggests that all conductive structural metal parts forming an integral part of the below-grade enclosure be bonded to the grounding system. There are several technical reasons for this requirement. Firstly, safety. Bonding steel columns helps to ensure that all metal components of the building, including the steel framing, maintain the same electrical potential. This minimizes the risk of electric shock hazards and promotes the correct operation of electrical equipment. Secondly, lightning protection. Bonding steel columns provide a low impedance path that allows lightning currents to safely discharge into the ground. This safeguards the building and its occupants for potential lightning damage. Thirdly, grounding system integrity. Bonding steel columns reinforces the continuity of the ground ring, offering a reliable path for both fault currents and lightning currents. Despite these guidelines, exceptions may exist. In some scenarios, bonding individual steel columns might be unnecessary. For instance, if the steel columns are already connected to the ground ring via a continuous steel frame, additional bonding of each column could be redundant. To determine the specific requirements for a project, it is always recommended to consult with a local building code official and a qualified electrician. Their expertise ensures compliance and safety. The importance of a grounding system cannot be overstated, as it serves as a critical safety measure in electrical installations. Its primary function is to provide a low impedance path for fault currents to return to the source, thereby tripping the circuit breaker or fuse and energizing the circuit. This rapid response minimizes the risk of electrical shock and equipment damage. A well-designed grounding system also helps to stabilize voltage levels, reduce electrical noise, and prevent the buildup of static electricity. The main components of a grounding system typically include a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is a conductive rod, plate, or mesh buried in the earth that provides a direct connection to the ground. The grounding electrode conductor connects the grounding electrode to the main electrical panel. Equipment grounding conductors are wires that connect the metal enclosures of electrical equipment to the grounding system. These conductors provide a path for fault currents to flow back to the source, tripping the circuit breaker or fuse. There are several types of grounding systems, each with its own advantages and disadvantages. The most common types include the solid grounding system, the impedance grounding system, and the ungrounded system. In a solid grounding system, the neutral point of the transformer or generator is directly connected to the ground. This type of system provides a very low impedance path for fault currents, resulting in rapid clearing of faults. However, it can also lead to high fault currents, which can damage equipment. In an impedance grounding system, an impedance, typically a resistor or reactor, is inserted between the neutral point of the transformer or generator and the ground. This impedance limits the fault current, reducing the risk of equipment damage. However, it also slows down the clearing of faults. In an ungrounded system, the neutral point of the transformer or generator is not connected to the ground. This type of system does not provide a path for fault currents, so faults can persist for a long time without being detected. However, it is less likely to experience high fault currents. The selection of the appropriate grounding system depends on the specific application and the desired level of safety and protection. Factors to consider include the size of the electrical system, the type of equipment being used, and the potential for fault currents. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Grounding electrodes should be checked for corrosion and damage, and grounding conductors should be tested for continuity. Any problems should be promptly corrected to maintain the integrity of the grounding system. In addition to bonding steel columns, other metal parts of the building should also be bonded to the grounding system. These include metal water pipes, gas pipes, and other metallic structures. Bonding these parts helps to ensure that all metal objects are at the same electrical potential, reducing the risk of electric shock. When designing and installing a grounding system, it is important to follow the requirements of the National Electrical Code, as well as any local codes or regulations. These codes provide detailed guidance on the selection of grounding electrodes, the sizing of grounding conductors, and the installation of bonding connections. Proper grounding is a critical aspect of electrical safety. By following the guidelines and recommendations outlined in this discussion, one can ensure that the electrical system is properly grounded and that the risk of electrical shock and equipment damage is minimized. In the context of steel buildings, the steel structure itself can be utilized as part of the grounding system. This is often achieved by connecting the steel columns and beams to the ground ring or other grounding electrodes. When using the steel structure as part of the grounding system, it is important to ensure that all connections are properly made and that the steel is free of corrosion. Corrosion can increase the resistance of the connections, reducing the effectiveness of the grounding system. The size of the grounding conductors and bonding jumpers must be adequate to handle the expected fault currents. The National Electrical Code provides tables that specify the minimum size of grounding conductors based on the size of the electrical service. Bonding jumpers should be sized according to Table 250.104C of the National Electrical Code. It is also important to consider the potential for lightning strikes when designing a grounding system for a steel building. Lightning strikes can generate very high currents, which can damage equipment and cause fires. A properly designed grounding system can help to protect the building and its occupants from lightning damage by providing a low impedance path for the lightning current to flow to ground. In addition to grounding, bonding is another important aspect of electrical safety. Bonding is the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current. Bonding helps to ensure that all metal objects are at the same electrical potential, reducing the risk of electric shock. Bonding is typically required for metal enclosures, metal conduits, and metal equipment frames. Bonding jumpers are used to connect these metal parts together. The size of the bonding jumpers must be adequate to handle the expected fault currents. The National Electrical Code provides tables that specify the minimum size of bonding jumpers based on the size of the electrical circuits. Grounding and bonding are essential for electrical safety in steel buildings. By following the requirements of the National Electrical Code and other applicable codes and standards, one can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electrical shock and equipment damage. The installation of a ground ring around the perimeter of a building is a common practice for enhancing the grounding system. The ground ring is typically a bare copper conductor that is buried in the earth around the building. It provides a low impedance path for fault currents to flow to ground. The ground ring is typically connected to the building's grounding electrode system, which may include ground rods, metal water pipes, and the building steel. The ground ring helps to equalize the ground potential around the building, reducing the risk of electrical shock. It also provides a path for lightning currents to flow to ground, protecting the building from lightning damage. The installation of ground rods is another common practice for enhancing the grounding system. Ground rods are typically copper or copper-clad steel rods that are driven into the earth. They provide a direct connection to the earth, which helps to dissipate fault currents and lightning currents. Ground rods should be installed at least 8 feet deep and should be spaced at least 6 feet apart. Multiple ground rods are often used to improve the effectiveness of the grounding system. The connection to the water pipe is another important aspect of the grounding system. The metal water pipe provides a low impedance path for fault currents to flow to ground. The water pipe should be connected to the building's grounding electrode system with a bonding jumper. The bonding jumper should be sized according to the National Electrical Code. The connection to the building steel is another important aspect of the grounding system, as discussed earlier. The building steel provides a lower impedance path for fault currents to flow to ground. The building steel should be connected to the building's grounding electrode system with a bonding jumper. The bonding jumper should be sized according to the National Electrical Code. In summary, the grounding system for a building typically includes a ground ring, ground rods, a connection to the water pipe, and a connection to the building steel. These components work together to provide a low impedance path for fault currents and lightning currents to flow to ground, protecting the building and its occupants from electrical shock and equipment damage. Regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Grounding electrodes should be checked for corrosion and damage, and grounding conductors should be tested for continuity. Any problems should be promptly corrected to maintain the integrity of the grounding system. It's also important to remember that electrical codes and regulations can vary depending on the location. Always consult with local building code officials and qualified electricians to ensure that the grounding system meets all applicable requirements. They can provide specific guidance based on the unique characteristics of the building and the local electrical environment. Table 250.104c in the National Electrical Code provides guidance on the size of the bonding jumper required for bonding metal water piping systems and other metal piping systems. The table specifies the minimum size of the bonding jumper based on the size of the service entrance conductors or the equivalent size of the conductors for a separately derived system. The purpose of this bonding jumper is to provide a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and energizing the circuit. This helps to prevent electrical shock hazards and equipment damage. The bonding jumper should be installed in accordance with the National Electrical Code and should be accessible for inspection and maintenance. It is also important to ensure that the bonding jumper is properly connected to the metal water piping system and to the building's grounding electrode system. The connection should be made with approved connectors and should be protected from corrosion. In addition to bonding metal water piping systems, it is also important to bond other metal piping systems that may be present in the building, such as gas piping systems and sprinkler piping systems. These piping systems can also provide a path for fault currents to flow to ground, and bonding them helps to ensure that all metal objects are at the same electrical potential, reducing the risk of electric shock. The IEEE 1100 standard, also known as the Emerald Book, provides recommendations for power and grounding sensitive electronic equipment. Section 10.3.10 of the standard addresses the bonding of structural metal parts to the grounding system. The standard recommends that all conductive structural metal parts that form an integral part of the below-grade enclosure be bonded to the grounding system. This includes steel columns, beams, and other structural members. The purpose of this bonding is to provide a low impedance path for fault currents to flow back to the source, tripping the circuit breaker or fuse and energizing the circuit. This helps to prevent electrical shock hazards and equipment damage. The IEEE 1100 standard also recommends that the bonding connections be made with approved connectors and that they be protected from corrosion. The standard provides guidance on the selection of appropriate bonding conductors and connectors. In addition to bonding structural metal parts, the IEEE 1100 standard also recommends bonding other metal objects in the building, such as metal water pipes, gas pipes, and conduit. This helps to ensure that all metal objects are at the same electrical potential, reducing the risk of electric shock. It is important to note that the IEEE 1100 standard is a set of recommendations, not a set of requirements. However, following the recommendations in the standard can help to improve the safety and reliability of electrical systems. When designing and installing a grounding system, it is important to consider the specific needs of the application and to follow the applicable codes and standards. The National Electrical Code provides detailed guidance on grounding and bonding requirements, and the IEEE 1100 standard provides additional recommendations for sensitive electronic equipment. By following these guidelines, one can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electrical shock and equipment damage. Lightning protection systems are designed to protect buildings and other structures from the damaging effects of lightning strikes. A lightning protection system typically consists of air terminals, down conductors, and a grounding system. Air terminals are metal rods or conductors that are installed on the roof of the building. They are designed to intercept lightning strikes and to safely conduct a lightning current to ground. Down conductors are heavy gauge wires or cables that connect the air terminals to the grounding system. They provide a low impedance path for the lightning current to flow to ground. The grounding system consists of ground rods, ground plates, or other grounding electrodes that are buried in the earth. It provides a direct connection to the earth, which helps to dissipate the lightning current. When lightning strikes a building, the lightning current flows through the air terminals, down conductors, and grounding system to the earth. The grounding system dissipates the lightning current, preventing it from damaging the building or its contents. A properly designed and installed lightning protection system can significantly reduce the risk of lightning damage. The National Fire Protection Association, NFPA, publishes a standard for lightning protection systems, NFPA 780. This standard provides detailed guidance on the design, installation, and maintenance of lightning protection systems. It is important to follow the requirements of NFPA 780 when designing and installing a lightning protection system. In addition to protecting buildings from lightning strikes, lightning protection systems can also protect electronic equipment from lightning surges. Lightning surges are brief, high-voltage spikes that can damage or destroy electronic equipment. Surge protective devices, or SPDs, are used to protect electronic equipment from lightning surges. SPD are installed in electrical panels and at the point of use. They divert the lightning surge to ground, protecting the electronic equipment from damage. It is important to use SPD that are specifically designed for lightning protection. These SPD are typically rated to withstand high surge currents. Lightning protection systems are an important part of electrical safety. By following the guidelines and recommendations outlined in this discussion, one can ensure that the building and its contents are protected from lightning damage. It's also important to have the lightning protection system inspected and maintained regularly to ensure that it is functioning properly.